Welcome to this explainer. If you're a diploma student grinding through engineering technology, you already know math isn't just some abstract subject, right? It is quite literally the foundational blueprint of physical reality. Today, we're taking a really focused, academic yet minimalist journey into a totally crucial part of your engineering toolbox: ordinary differential equations. Our goal is to just strip away all the noise and help you master these essential blueprints like a professional. So let's dive right in. Here's our structured path for today. We'll start with the core problem, move on to equation anatomy, unlock the master key, apply it to electrical circuits, and finally look at the Laplace transform. Section 1. The core problem, modeling change. In engineering, things are almost never static. Systems evolve, temperatures drop, electrical currents flow. So how exactly do we mathematically model these rates of change in the real world? When a physical quantity is just constantly shifting, how do we capture that reality in a rigorous, solvable format? Well, the answer lies in differential equations. More specifically, we're looking at first-order differential equations. Basically, these are equations that involve the highest-order derivative of order 1. You can think of them as the universal language of change. Whether you're analyzing fluid velocity, figuring out the stress in a metal rod, or predicting how fast something cools down, you're mapping physical quantities over independent variables, like time or distance. Section 2. Equation anatomy. Homogeneous versus non-homogeneous. Okay, so before we can actually solve anything, we have to categorize it. There is one absolutely crucial difference between the two main types of linear equations. Homogeneous equations involve only derivatives of your dependent variable, let's just call it y, and terms involving y, and they're set exactly to 0. Non-homogeneous equations, they have a similar structure, but they include a non-zero function of the independent variable, like x or maybe a constant, right over on the right side. Spotting this difference early on is essential because it dictates exactly how we're going to solve the whole thing. Section 3. The master key. Integrating factor. So once you've identified a linear first-order equation, how do you actually crack it? Well, it follows a super reliable 3-step procedure. Step 1. Write the equation in standard form so that the first derivative is standing completely alone. Step 2. Calculate your integrating factor. And step 3. Multiply the equation by this factor, integrate both sides, and simplify. If you look at Stewart's calculus, they put it perfectly. To solve the linear differential equation, multiply both sides by the integrating factor, I of x, which equals e raised to the integral of p of x dx, and integrate both sides. This really reinforces the mathematical trick we're using here. Why do we do this? It's honestly brilliant. By multiplying both sides of our standard form equation by this one specific function, the entire left side magically collapses into the exact derivative of a product, your integrating factor times your dependent variable. It literally transforms a seemingly impossible calculus problem into a straightforward integration task on the right side. Section 4. Real-world execution, electrical circuits. Let's see how this actually operates in the physical world. Think about standard series RL and RC circuits. These are first-order circuits, meaning they only include one energy storage element. When we sit down to analyze their dynamics, like, say, tracking the current right after closing a switch, the mathematical result naturally forms a first-order linear ordinary differential equation. To bridge those physical components to our math, we rely on foundational principles. Kirchhoff's voltage law tells us that the algebraic sum of all voltages around any closed loop in a circuit must equal 0. This physical rule is exactly what gives us the starting equation we need for our mathematical modeling. Let's systematically break down the derivation for an RL circuit. Based on standard voltage-current relationships, the voltage drop across the inductor is proportional to the rate of change of current. We express that as L times di over dt. The voltage drop across the resistor, that's simply R times I. Equating this to our source voltage, Vs, gives us our KVL equation. L times di over dt plus R times I equals Vs. Now remember our master key steps. We have to get this into standard form. By dividing every single term by L, we get di over dt plus R over L times I equals Vs over L. This setup nicely reveals the time constant, tau, which is L divided by R. And with the equation in standard form, you're perfectly set up to find that integrating factor and solve for the current at literally any given time. Section 5. The ultimate shortcut. Laplace transform. Engineering is definitely going to throw you some curveballs, like switches creating discontinuous inputs. For those, we need a slightly more advanced technique. Enter the Laplace transform. It's an integral operator, but honestly, you can just think of it like a master language translator. It takes a really difficult calculus problem in the time domain, which we represent with t,
and it translates it into a much simpler algebraic equation in the frequency domain, represented by S. So instead of doing complex integration, you're just doing basic algebra, solving for your variable, and then translating it right back. It's a real game changer.
To make sure you have a really clear, reliable guide for your coursework and exams, here is the basic checklist for using the Laplace method. First, apply the Laplace transform to each term in your differential equation using your standard lookup tables. Second, and this is a huge advantage over other methods, immediately plug in your initial conditions at t equals 0. You don't have to wait until the end. Third, simplify the equation algebraically to isolate your transformed variable. And finally, use inverse Laplace transforms and maybe some partial fraction decomposition to translate your answer back into the time domain to get that final solution. We've covered a lot of ground today: the core structures, the integrating factor, practical circuit models, and the Laplace transform. You now have a robust, minimalist framework for tackling these concepts. So I want to leave you with a provocative thought. As you step out of the classroom and really start analyzing physical systems, circuits, and fluid dynamics in your engineering trades, what hidden differential equations are waiting for you to solve them? This math isn't just theory anymore. It's literally your ultimate tool for designing the future. Thanks for joining me in this explainer. Keep analyzing, keep calculating, and we'll see you next time.